Hi everyone. Today's topic I'd like to introduce to you is numerical estimation of roots, and this is part of your Mathematics Extension 1 syllabus. Now, firstly, you might think, why do we even need numerical estimation of roots? We have algebra, we have the quadratic equation, we have lots of methods to work out roots in equations. So normally when you see an equation like x squared plus 2x plus 1 equals to 0, for example, we would just factorize it and find the roots. But there's actually, in reality, a lot of equations for which there's no way for us to actually work out the roots mathematically. So example of that is we have e to the power of sine x equals to x squared, for example. So we just can't work out the roots between that. And this is when we need our numerical estimation. So a method to estimate the roots in between them. And today I'm going to go through two types of numerical estimation. So the first one is called halving the interval method, and the next one will be called Newton's method. So let's firstly start off with halving the interval method. So how we work with numerical estimation is, for example, not quite sure what this graph looks like, but it might look something like that. And what we do in halving the interval method is we take two values. So let's say this value here, and you can see that's positive, and this value here, and you can see that's negative. Now, because this is positive and this is negative, what we assume is that this graph has to cross the x-axis to go from positive to negative, right? And we're taking advantage of that fact to estimate that the root has to lie between this value and this value, yeah? And then we try and narrow it down until we find a narrow interval to work that out, okay? So that's how halving the interval method works. So as it suggests, by halving the interval, we literally take half of that. So let's say this point here, and we test it, and we find out that it's positive, again, we now know it must lie between our new positive and this negative. So now we can exclude that entire section here and just concentrate on this part, okay? And now we've narrowed the interval. So what I want to go through now is that sometimes, as with any estimation method, there's going to be problems to it. And what can happen is when you have too wide an interval is when a lot of the problems occur. So let's, for example, say that with that graph, yeah, we had this point here, which was positive, and then we had this point here that was negative. Okay, and for this case, there is a root in the middle, but sometimes this can happen. So even though that this is positive and this is negative here, as you can imagine, you could get something like this. Okay, so still you have this value that's positive and a value that's negative down here, but what you actually now have is three roots in the middle like that. Can you see how, because it's too wide, we actually have multiple roots in between? And so that's why we really need to know about how intervals need to be chosen correctly to get our most appropriate estimation. All right, let's have a look more in detail about halving the interval method. So this is just a brief overview of what I just explained. So what we have here is A, which is negative, yeah, and B, which is positive. So we can say that they have opposite signs. And because they have opposite signs, we assume that to get from this positive to that negative, it has to somehow cross the x-axis. So that's why we say there should be a root in between somewhere, A and B, okay? And also because they have opposite signs, so one's negative and one's positive, we can also say that when you multiply them together, it should be negative or less than 0. So let's take another look at an example of this. So in this case, now A is positive, you can see that up here, and B is negative, you can see that down there. And we're assuming that it has to cross somewhere in between A and B to have a root because it has opposite signs. Now, this is what I was explaining before. So in this case, while A is still negative and B is positive, so they have the opposite signs, what we have is too wide an interval, and now we have multiple roots in between A and B. Yeah, so you can see here we actually have 3 roots in between, and so if we say interval between then, we can't say which root it is. When you can actually avoid that, as you can see, just by narrowing it down. So if you had B over here that was positive, then you would only have 1 root. Okay, so that's why we always try and narrow our intervals down. So this is another way that you can have multiple roots. So in this case, we have A negative, B positive, so they have opposite signs, but there's multiple roots in between here because, as you can see, that's actually an x cubed graph. So this could be, for example, x minus 1 cubed. So x is going to equal to 1, 1, and 1. So there's actually 3 roots in between those 2 values. And as you can see with this one, unfortunately, no matter how narrow you make this interval, there's always going to be multiple roots in between them, because that root itself is a multiple root. So what this is showing is limitations of your estimation method. Okay, sometimes you can try as hard as you can with intervals, but there will be failings of any estimation method. Okay, so we just went through multiple roots. Now what I want you to understand is just because A is negative and B is positive and they have opposite signs, sometimes there's actually no roots at all in between them. And this can happen, for example, here when you have a hyperbola. So you have B is positive, but that's moving away. And A is negative there, but that's moving away there. So there's actually no root between A and B. Can you see that? Yeah? So no root actually lies between them, even though they have opposite signs. Okay, so we've just gone through all the ones with opposite signs. Now I want to have a look at what happens when things have the same sign. So part of halving the interval method is we assume that when 2 values have the same sign, so for example here, A is positive and B is positive, that no root is going to lie between them. So we try and assume that. But as with our opposite signs, there's going to be some limitations to that, and that's what I'm going to show you now. So in this one, we can see again, A is positive and B is positive, and this is normally what happens. So because they're positive, we're going to say there's no root between them. And similarly here, A is negative and B is negative, so they have the same sign, and because of that, no root is going to be there. But sometimes this happens, and this usually happens when you have too wide an interval. So A is positive and B is positive, and they have the same sign, but you actually have 2 roots in the middle that you may have missed if you just eliminate that because you say it has the same sign. Can you see that? That, because it's too wide, you've missed those 2 roots. So you can stop that from happening if you have a narrower interval. So for example, if B was there, yeah, then you're not going to have that problem as often. Now, multiple roots can also occur in this example here, where you have A is positive and B is positive. And because this just happens to touch the x-axis, right, you're going to have a root in between A and B when they have the same sign. And that's something that you can't avoid because, as you can see with this example, even if we had 2 very narrow intervals that were both positive, we're still going to miss that root using this example. So in summary, what I really want you guys to know is that it's extremely important to find good intervals to find your appropriate estimation of the root. Now, what you don't need to know is how to find these intervals. But what you do need to know is what can go wrong by using this estimation method. And that's because what happens is some of the questions they'll ask you is they'll say, well, someone has used this halving the interval method and they've worked out that at 2, it's positive, yeah? And then at 3, it's negative. Now, why is there no root between a positive and a negative? And this is when you use all the knowledge that I just taught you and say, well, maybe it's a hyperbola, so that's going like that, and this is going like that. And that's why there's no root in between. Or it might ask you to explain, we have two positives, yeah, and there's still a root in between. Why is that? Okay, so that's how we use all that knowledge over there. All right, excellent. Okay, let's go through some examples together now. So here we have scenario 1, and we want to test whether the root lies between 1 and 9. So this is just us trying to get familiar with halving the interval method. So firstly, all you need to do is test 1, substitute it into the equation. You find out that it's greater than 0. And you test 9 and find out that's less than 0. So we get a general idea that this graph looks something like this, okay? So this root has to lie anywhere between 1 and 9. And this is when we halve the interval. So knowing the root lies between 1 and 9, we take half of 1 and 9, which happens to be 5, and we test this new interval there. In testing 5, we find it to be negative, okay? And so now we know that since this is negative and this is positive, that the root lies between 1 and 5. So we just eliminate that area there, okay? Because they were both negative, so we assume it's not going to be between there, and it's going to be between 1 and 5, yeah? Can you see how now we've narrowed that interval between 1 and 5 now? Yeah, exactly. All right, let's test that again. So halving the interval again between 1 and 5 is 3. So testing 3, we find out that it's positive, okay? So now we have this positive and this negative, so we say it's probably going to be between them, which means since a root lies between 3 and 5, we can now eliminate between the two positives, all right? So now we've narrowed that interval again. And since we have a narrow enough interval now between 3 and 5, what we can do is take the approximation of the root. And how we do that is the same method as halving the interval. So we just take between 3 and 5, which is 4, and we say 4 in this case is approximation of the root. And that in this case is enough, so we're not going to keep going, and that's where we're going to stop. All right, let's move on to scenario 2 now. So in scenario 2, we want to again test whether the root lies between 1 and 9. And what I want to demonstrate to you in scenario 2 is just because a root lies between 1 and 9, it doesn't always have to lie in the middle. So it could lie anywhere from over there, so on one side, or for example, it might be on the other side as well. And that's what I want you to keep in mind. That I don't want you to assume just because it's between two roots that it has to be smack bang right in the middle. Okay, let's do our methods now. So 1, we find out is negative, and 9 is positive, okay? So not quite sure, but maybe something like that. And now we halve the interval between 1 and 9, so that gives us 5. And testing that, we find out that 5 is less than 0, so it's negative as well, okay? So this is negative, that's positive. It's going to lie between this interval here. It's going to lie between 5 and 9, which means we can eliminate between 1 and 5. All right, okay? Halving the interval again between 5 and 9 is 7. So substituting 7 into the equation, you find out 7 is negative as well. So it's probably not going to look like that anymore because 7 is negative as well, which means the root now is going to lie between 7 and 9. So something like that, okay? Which means we get rid of 5 to 7. It's not going to be there. And that's enough of an estimation. And now we can just say the approximation of the root is between 7 and 9. So it's going to be 8. And this was what I was demonstrating to you before. When we first started off, we were saying it's between 1 and 9. And as you can see in this case, it's actually much to the side. So it's 8 rather than in the middle of 5 or 4 or 6. Okay? So it could be anywhere between 1 and 9. It doesn't have to be in the middle. All right. Great, so now we've gone through some examples. I want us to work through some questions together now. So starting off with question 1 here, we have this equation of x cubed minus 3x squared plus 3x minus 3, and I want you to complete the table for this. So we're just, taking the hard work out for you here, and we've worked those values out already. And we find that these are negative and these are positive, okay? And between 2 and 3 is when it switches from negative to positive. So negative there and positive there. So by using the halving the interval method, we know that the root should lie between 2 and 3. Yeah, because we're going from a negative to positive, so it should cross the x-axis at some point. And when we look at the actual graph for this, you can see it's going from negative to positive, and there is actually a root right there between 2 and 3. Can you see that? Yeah? So therefore, we've shown that the root lies between 2 and 3 because the f of 2 and 3 have opposite signs. Now, you don't need to know how to draw this graph perfectly, but we've just shown that to you to show how the estimation method does indeed work out the right root in this case. Great. Let's move on to B now. So here we actually want to find the root for this equation, and it tells you using 2 applications of halving the interval. Now, there's 2 types of questions that you're likely to get. So the first type is when it tells you exactly how many applications to use. And in the next question, when we get up to that, you'll see that you have to work out for yourself how many applications you do need to use. Okay, so from part A, we knew that since 2 was negative and 3 was positive, that it's going to lie somewhere between 3 and 2. Not quite sure how, but something along those lines. So now we just halve the interval. So your first application is counted from your first halving of the interval. So in this case is 2.5. And testing that just by substituting it straight into that equation there, we find out that it's positive. So 2.5 in this case is positive. So now we can say the root is going to probably lie between 2 and 2.5. Yeah? So we can just get rid of that section there. So now I know it's much more likely to look like this than what I drew before. And now we do the second application, all right? So that's when we halve the interval again. So between that is 2.25. And just substitute that straight into the equation, and we work out that it's negative in this case. Yeah? And if it's negative there, it must be between the negative and the positive. They have opposite signs, so the root lies between them. So now we can eliminate between 2 and 2.5. So it's going to be in between there like that. And we've worked out our 2 intervals, applications, so now we just need to approximate. So between that is 2.375. So that is our approximation of the root in this case. All right. Good, so this was the example when he told you exactly how many applications you needed to use. Let's have a look at question 2 now. So here we want to show this equation has a root between 3 and 4. So how are we going to do that? All right, very easy. All you need to do is substitute 3 into the equation and work out that that's right, it's going to be negative, and 4 into the equation and show that it's 3, so it's going to be positive. And since they have opposite signs here, we can say, thus the root lies between 3 and 4. Nice and simple, right? Good, let's move on to part B now. So here, we want to use a method of halving the interval to find the root, correcting to 1 decimal place. So the important phrase here is 1 decimal place. So you can see, it doesn't tell you how many applications you need to use. We need to work that out for ourselves. Now, that phrase 1 decimal place confuses a lot of students, and I don't blame anyone because it actually does get a little bit misleading. So what it doesn't refer to is if we took half the interval here, it's going to be 3.5. Okay, and some people might think, oh, well, that's 1 decimal place. So once we found that, it's between 3.5 and 4, and since one of them has 1 decimal place, that's all we need to do. No, definitely not. what that one decimal place refers to is you need two intervals that round to the same number correct to one decimal place. Okay, so for example, if we kept halving the interval more and more until, for example, we got two values. So let's just say we had something here which was 3.45 and another interval here which was 3.53, for example. Can you see how both of those values round to 3.5? That would round to 3.5 and that also rounds to 3.5. So those two intervals agree to the same one decimal place, okay? And that's when we can say that 3.5 is the root to one decimal place, because it must be, because it's between those two that both round to that. Can you see that? So all you need to know for this is that you just want to find two intervals that agree to the same one decimal place. Yeah, and I think that's the easiest way to think about this. All right, let's actually work out the value now instead of me just guessing over there. So halving the interval here at 3.5, we just substitute that value into our equation before and find out that it's positive in this case. So if it's positive, then the root should lie between 3.5 and 3, okay? Between the positive and negative, like that. And we can just eliminate this area when they were both positive. Now, having a look at that, they definitely don't agree to the same decimal place, so we want to halve the interval again. So now 3.25. And substituting that in, we find out that it's negative in this case. All right, so now it's going to lie between 3.25 and 3.5. They're the opposite signs there, which means I can eliminate this area over here, and I know it's got to be something between there, okay? Not sure where. Now, having a look here, you can see that this is going to round to 3.3. It could also be 3.4 or it could be 3.5. We don't know which one. Yeah, so it doesn't agree to one decimal place yet. So that means keep going. Halve the interval again. Okay, halving again, we find it's 3.375. Substituting that in, it's positive, which means that it must lie between those two values, and we just eliminate the interval between the two positive intervals. All right, let's have a look at these two values again. So this rounds to, 3.3, and that rounds to 3.4. So again, they don't agree to the same one decimal place yet, which means, that's right, got to keep going, okay? So halve that interval again, and that's going to be 3.3125, getting very narrow intervals here. And we're going to substitute that into the equation. We find that's positive now, all right? Which means I can eliminate that area over there because I know the root must lie between these two values. So it's going to lie in between like that. And now when I look at these two values, I can see that both 3.25, that's going to round to 3.3, and 3.3125 rounds to what? Exactly 3.3. So can you see how they agree now? They equal each other. So that's how I can say that therefore the root has to be 3.3 correcting to one decimal place. So this is the most common mistake that students make, and as long as you remember they just need to agree to the same one decimal place, you should be fine for these questions.